This is Mrs. James. This is a video summary for the Waves chapter for Science 9. This is a short summary of actually parts of two different chapters from the books. Strongly encourage the students to read both of these chapters. A couple foundational ideas in this section. 1. Energy travels from one location to another in the form of waves. Second, there are different kinds of waves. Third, waves can have characteristics that can change. And fourth, waves can be affected by objects. Alright, two different types of waves are called transverse and longitudinal. Here's a picture of both of them. This kind is called transverse. The word trans comes from the idea of being across, so it cuts across the direction of the flow of energy. And longitudinal, it goes along, not across. So these are being demonstrated with slinkies. If these are actual waves, in this example right here, longitudinal, it's actually molecules of air or of water or whatever the material is. We call that material the medium, that are getting pushed close together and being spread farther apart. In a transverse wave, there doesn't have to be any matter for this wave to go. It's just that the energy itself travels in this pattern. A couple important words to know. One is wavelength. Here you see a wavelength is from one point of a transverse wave to another, and in a longitudinal wave it's from one spot to a similar spot on the next wave. Light, ultraviolet light, infrared heat, these things travel in a transverse wave, and sound is the thing that we're mostly talking about that travels as a longitudinal wave. Here's another picture of a transverse wave. Even though sound waves travel as longitudinal waves, for simplicity of drawing, we normally use a transverse model when we draw them. This is showing you a few more vocabulary words. Here's a wavelength. Peaks are called crests. Bottom parts are called troughs. One complete cycle is a wavelength. And from the midline to the top of the crest, or from the midline to the bottom of the trough, is called the amplitude. Amplitude is associated with loudness in sound or brightness in light, and wavelength and frequency. So bigger the wavelength, smaller the frequency. Smaller the wavelength, the bigger the frequency. Those are associated with pitch for sounds and colors with light. Alright, sound. Longitudinal waves are called by vibrations. Speed depends on the medium. How fast can the medium transmit the compressions and the rarefactions? So these molecules are bumping into each other. How quickly can that happen? That tends to happen quicker in solids and liquids than in gases because the molecules are closer together. Loudness is determined by intensity. Units are decibels, and that's also what we were talking about, amplitude, on the previous page. So here's a picture of a wave that has low amplitude. Again, remember that sound waves are actually longitudinal. We're just drawing it as a transverse wave for simplicity. Pitch is determined by the frequency of the sound waves. Here's two waves for comparison. This is a low frequency wave. This is a high frequency wave. This would have a high pitch. This would have a low pitch. We also talked about another idea called Doppler effect. This is in the book. There's also a really nice website here about it. I suggest that the students check out this website and read about it in the book. Light. We're going to come back to this page in a minute. Energy coming from the sun is called the electromagnetic spectrum, and it's determined by the size of the wavelength or the frequency. So big waves that have a big wavelength and a small frequency we call radio waves. Progresses through, again, all these energies are coming from the sun. When they have a high frequency and low wavelength, we call those gamma rays. And right in here is the portion that we call visible light. So these are the colors that we can actually see with our eyes. And so red colors have got a little bit longer wavelengths, and violets have got smaller wavelengths. When light hits an object, three things can happen. It can be reflected, absorbed, or transmitted. When it's absorbed, it goes through a transformation of energy and it gets changed into heat energy. Usually when light hits an object, some of the wavelengths get reflected and some of them don't. What gets reflected is what we see as a color. So if an object is white, none of the colors are absorbed. They're all reflected, so you see all those colors together, which our mind registers as white. If just if everything except red gets absorbed, the red bounces off and you see that object is looking red. If all the colors get absorbed, nothing bounces off and you see it as looking black, and then it's going to get very warm. That's why blacktop is hotter on a bright day than, say, a white surface. Okay. If the surface is very smooth, it tends to make it shiny. For instance, a mirror or the surface of water. If the surface is very rough, then the light tends to be scattered in all directions and it's not reflective. The law of reflection is pretty basic. If you have a surface and a wave hits it, and we're going to show our wave like this, the angle that it comes in is equal to the angle that it bounces off. So this angle is equal to this angle. It bounces in at this angle, it's going to bounce back off at that angle. And these are usually measured against a imaginary line that's parallel to the surface, like so, and that's called the normal. So the angle in compared to the normal is equal to the angle out. Alright, sometimes the light goes through an object, like if it hits a mirror or if it hits water. And when that happens, it's normally what we call refracted. And refracted means it changes direction. So here's our surface, like so. If the light comes in, or the waves come in at this angle, they will leave and travel a different angle, a different direction than the new surface. And that's what happens because they change speed. This causes a couple of phenomena, like if you look at your glass of water from the side, your straw looks like it's been displaced above and below the water. Or if you're trying to spear fish and you aim at the fish, you're actually going to miss it because the refracting light makes the fish look like it's not. Students did a lab on this and they can remember in the lab how they couldn't aim quite at the fish if they wanted to hit it. Alright, let's go back to the other slide for a minute. Alright, lenses take advantage of refraction to change the positioning of an object. There's lots of different types of lenses. We're really not going to go to a detail on this in class. That would be a whole chapter in a physics class. Could be a cover on lenses. You could have a whole multiple weeks, even a whole course on lenses at the college level. Mirrors take advantage of reflection to change images. Alright, sometimes when waves are reflected they encounter another wave. We're going to skip this material for right now. Let's talk about waves hitting each other. So if an object bounces off another object, if a wave bounces off an object, it may go shooting around the room, bouncing off the different walls, or bouncing off different surfaces. And sometimes when that happens, it's going to hit other waves. So here's an example of two waves hitting each other. We call that interference. And in this particular example, when the two waves hit each other, the crest of one wave is lined up with the crest of the other wave. So you can see that right here. Crests are lined up like that. And when that happens, the effect is additive, and for just a moment in time, you have an extra big wave where those two waves hit each other. So it would be like this. This wave is traveling this way. This wave is traveling this way. They hit each other when they're aligned, and you get the big wave. That's called constructive interference. If we're talking about sound, the sound would be temporarily louder. If we're talking about light, the light would be temporarily brighter. Sometimes when they hit each other, though, the waves are not aligned. So we're showing that here. When these two waves hit, their crests aren't aligned. That would be if these waves are traveling towards each other, and when they hit each other, they hit like that. Well, in that particular case, the amplitudes can reduce each other and even wipe each other out. So this would be, for sound, this would get quiet or completely silent. If this was light, it would get less bright or even completely dark. And of course, it's usually not that complicated. Usually the waves aren't the exact same amplitude. Usually they don't hit dead on, so this is just a basic example. There's some great pictures of this in the book also. This is one of the harder ideas that's in this chapter. There are a ton of Google sites about this one, so you can look up what's constructive interference of waves, what's destructive interference of waves, and you'll get lots of really good animations on that. Here is a list of possible websites you might want to check out. Okay, talking about the two wave types: virtual slinky that you can use and animate yourself, law of reflection, website of refraction, superposition, and interference. So these two are talking about that positive, constructive interference and destructive interference.